Great. Well, thanks for the invitation. It's nice to be here and no longer be waiting in silence. I'm going to talk today about some joint work that was largely first envisioned here at the Hausdorff Institute 2 years ago in the summer program, in the trimester program on homotopy theory. So this is all joint work with David Gepner and Jeremiah Heller. And let me just get into it, and then I'll sort of come back and explain why we're doing what we're doing. So I'm going to put on the board 3 conjectures. So this first is due to Schlichting. So if A is an abelian category, then the negative K groups of A are 0. So these negative K groups can be realized as the K groups of some kind of triangulated category, the bounded derived category of A. And from our perspective, this can be realized as the homotopy category of a stable infinity category or a pre-triangulated DG category. And this has something called a T structure that's bounded because I wrote B here. So this motivates conjecture B, which says that if C is a stable infinity category, and I'll say a little bit about this, with a bounded T structure, then the negative K groups of C also vanish. So this is just literally a strict generalization of this conjecture. And now conjecture C relates these two to the theorem of the heart of Clark-Barwick. So it says if C is a stable infinity category with a bounded T structure, so one sort of thing to know about something with a T structure is that there's an abelian category involved called the heart. And there's an induced map from the K-theory spectrum of the heart to the K-theory spectrum of C. And the conjecture is that this should be an equivalence. So let me say a little bit about what's known. OK, so let me just make a remark about stable infinity categories. So you can really think about these are some kinds of models for triangulated categories. And maybe many people in the audience are more familiar with DG categories. So these would be the sort of pre-triangulated DG categories. So if you can just, in your head, swap stable infinity category with pre-triangulated DG category if you wish for this talk, or you could probably even safely think of this as just a triangulated category. So don't let this be too mysterious. And giving a T structure on such a thing is equivalent to giving a T structure on the triangulated homotopy category. So you can express what it means to give this T structure only in terms of sort of homotopy category theoretic information. And so if you have the homotopy category in a T structure, that gives a T structure on the infinity category in this sense. OK, so this is purely, the definition of this comes purely back to things that are familiar from like triangulated category things. So let me say a little bit about what's known so far about these 3 conjectures. So A is true. Well, OK, maybe that looks a little bit bad. So conjecture A is true for n equals 1. So k minus 1 of any abelian category vanishes always. Conjecture A is true for all n when A is Noetherian. And these two facts were proved by Schlichting in his paper on negative K-theory of exact categories, or whatever he called that. So let's see. Part of our motivation for posing conjecture C is that for the connective part, this is a theorem of Barwick. Which says that the connective K-theory of C Hart is always equivalent to the connective K-theory of C. And this is the so-called theorem of the Hart. And then finally, just let me put this implication. Conjecture B holds if and only if conjectures A and conjecture C hold. Pretty easy to see. Okay, so 20 minutes before the talk, decided to totally change the order. So I'm hoping to get to the point where all talks are invariant under, they're givable with any ordering of the pages. So we'll see if that's true today. So our contribution, so I mean, conjecture A is posed in Schlichting's paper. We suggest conjectures B and C. So our theorems, I don't know who that is. So the first one is that conjecture B is true for n equals 1. So this is the analog of fact A there. And the second theorem is that conjecture B is true for all n more than or equal to 1 when the Hart is Noetherian. In other words, we prove exact analogs of Schlichting's result when the T structure when there's a bounded T structure and the Hart is Noetherian for all negative groups and without any restriction for n equals 1. In particular, this recovers Schlichting's result, and the proof, while maybe philosophically similar, is rather different in details, sort of unsurprisingly, given the generality. So let me tell you a bit about that, but first let me say a few words about, how to think about some of these theorems. So you might think, well, okay, so the first is a remark that I think is pretty interesting. The property of possessing a Noetherian, a T structure with the property of possessing a bounded T structure with a Noetherian Hart is a very strange one. Okay, so the derived category of P1 over some field K. So this has a bounded T structure, right? Just where the Hart is coherent sheaves on P1. But it also has, for example, if K is the complex numbers, uncountably many other T structures where the Hart is not Noetherian. Okay, so this has many bounded T structures where the Hart is not Noetherian. For example, there's a T structure in which, there's one in which all of these are in the Hart. So this is OI shifted by 1 as a complex. And O0, 1 to O1, 1 to O2, 1. is an infinite sequence of epimorphisms in the heart. And so that means that the sequence of kernels, from here to here, then from here to here, and so forth, gives you an infinite increasing sequence of submodules of this in the heart, subobjects of this in the heart. This is a T structure associated to a torsion pair on the abelian in the initial abelian category. So, from this perspective, it probably makes it, hard to say whether a given stable infinity category yeah.
So there's a shift 1. For every I, you have the same shift?
For every I, you have the same shift, yeah.
So the new information is that these maps are everywhere?
Yeah. Yeah, right. Yeah, I mean, you can pick one section and then just keep composing. Any other questions?
Conjecture C hold for the other heart?
It's not known. Yeah. Yeah, I would.
Right.
I personally don't know.
So why did you put the square brackets with one, the shift of 1 in that example?
Just because these are in the heart, and the ordinary ones are not in the heart. In this.
But if you shift the T structure by 1.
Yeah. Okay. I mean, I could also do that, but I don't. When you write down, this is what pops out when you write down the most natural definition of the T structure of these T structures from the torsion pairs. Okay. Yeah. So another remark, and this is sort of this is in Schlichting, but Gabor noticed that that general abelian categories are not filtered colimits of Noetherian ones. Clearly, if they were, we wouldn't be talking about this. And it's pretty easy to write down examples of this. Okay, so finally, a remark that I think is maybe interesting in the context of this conference is, so suppose X is singular, some singular scheme, and consider the category of perfect complexes. Now, you know that the ordinary T structure on coherent sheaves is not going to restrict to a T structure on perfect complexes, because most OX modules, finally generated coherent OX modules, won't have bounded resolutions by locally free ones. So there's not an obvious T structure on this. And you might ask, because you're interested in maybe stability conditions or something like that, well, maybe there's some other T structure on this. And this theorem gives you an abstraction for that. So if k minus 1 x is not equal to 0, then there's no bounded T structure on perf x. And if k minus n x is not equal to 0 for some n more than or equal to 1, then there's no bounded T structure with a Noetherian heart. And I don't know how to prove this without something like this. I mean, I think that this I mean, maybe in the Artin local case, you could possibly say, but in that case, neither of these criteria would be satisfied. Okay. So this tells you that not only, is there not the obvious T structure, which is kind of known, but there's really no way to fix that problem. There's no other T structure that you could possibly put. On perfect complexes on a variety that has negative K-theory, especially K minus 1. And so, I think that's, given this example for P1 where you see sort of start to see how exotic these T structures can be, I think that that's a good reason to be interested about conjecture B in general, where you would then be able to say, well, if you have any negative K group, then you can't have any T structure at all, well, whether the heart's Noetherian or not. Now, am I supposed to dry this somehow? Well, maybe with this. It's kind of wet, though. I don't know. Let's see if this. Okay, this is probably not worth doing. Okay. So this could also potentially, there might be other categories you're interested in whether they have bounded T structures besides perfect complexes, and this could be used for understanding those as well. Here we go. Okay, so now let me say a little bit of background. So for us, K-theory is going to be a functor from this category to this category. So this is spectra. And this is the sort of an infinity category of stable, idempotent complete stable infinity categories, whatever these are. So the point is that there is such a functor, and that it basically agrees with the any other definitions of K-theory that you know when both are defined. So for an example, the K-theory of a ring or a ring spectrum R is going to be defined to be the K-theory of the category of compact R-module spectra. So just that is a small idempotent complete stable infinity category. You can take its K-theory. So this sort of approach is due to Blumberg, Gepner, and Tabuada. And there are two crucial properties that this functor satisfies. So K-theory commutes with filtered colimits. That's familiar property from basically all approaches. And the second is that it basically has a universal property. It takes these sorts of sequences to localization sequences. So this is going to be the idempotent completion of the Verdier quotient. So the idempotent completion. So whenever you have a sequence like this, you get a cofiber sequence of spectra. So here, A is a full subcategory of B, and it's a full stable subcategory or a triangulated subcategory at the homotopy level. This is a quotient that you can construct, just like in Verdier or something like that. So it's a specific, at the level of triangulated category. The homotopy category of this is the same as the usual Verdier localization. You compute maps using these sort of hats and so forth, and then you idempotent complete that. So such a sequence should give you a cofiber sequence of spectra. And these are basic, really B is the only thing that we're really going to use about K-theory besides the some sort of K0 computations. So, and then I'll define KCN, or tau more than or equal to 0 K, to be the connective covers. Okay, so why did we start thinking about this project? So to really tell the story of what we were doing at the time, I need to say something about, I'm going to ask a question about the K-theory of a ring spectrum that was our motivating problem. So the question that we were thinking about is K minus n of periodic Ku 0 for n at least 1? And let me tell you an answer to this that's not true, and to explain why we were confused. Any questions while I'm erasing? Well, yes. Oh, I should have said that. Right, let me put that remark here, which probably I was supposed to say anyways by now. So if R is a connective ring spectrum, which remember that means that pi minus nr is 0 for n at least 1, the negative homotopy groups are 0, then Blumberg, Gemper, Tabuada proved that the negative, really the non-positive K groups of R agree with the non-positive K groups of pi 0 of R for n more than or equal to 0. So for connective ring spectra, computing the negative K groups comes down to computing the negative K groups of pi 0. Ku, this is a ring spectrum with homotopy ring Z beta plus or minus 1, where beta is in degree 2. So this certainly does not fall under that theorem.
Is that category mod WR, that's the same as perf of R?
Yeah, exactly. If R is an ordinary ring, this would be equivalent to one model for perf R, precisely. Mm-hmm. Okay. So, well, the answer is, of course, yes. Is K, yes. So remember that there's this theorem of Blumberg and Mendel, usually stated as saying that there's a fiber sequence of spectra from the K-theory of Z to the K-theory of connective Ku. So pi star of connective Ku is isomorphic to Z adjoint beta. You just have an inverted beta to the K-theory of periodic Ku. Well, from what I just said, so K minus n of Z is 0 for n more than or equal to 1. K minus n of connective Ku is isomorphic to K minus n of Z by this result, and this is 0 for n at least 1 by the same fact. And that's going to imply that the negative K groups of this all vanish. But this is not actually a theorem yet until our results. So what we were confused about was basically that this theorem is in fact true with connective spectra. So what they prove is this. And let me explain where the difference comes from. So the difference comes from the fact that there's another fiber term that we can put here that's just is the fiber, no matter what, okay? So this is some kind of localization, so I can identify the fiber in, well, let me say it like this. So I can take mod of connective Ku omega, mod of periodic Ku omega, and this is a localization of that form. It's a map from a B to a C, and I can identify the fiber term no matter what. So the fiber term is what I'll say is mod of Ku omega beta acyclic. And this is a localization sequence. In other words, the compact objects that are killed, think about what compact Ku modules are killed when you invert beta. Well, they're exactly the beta torsion ones. So if beta acts nilpotently, then that's going to go to 0. And this turns out to be a localization sequence. And that means that there's a cofiber sequence just from this property B. Just from this property B, this implies that there, no matter what, there's a cofiber sequence of this form. And you know, if you wanted to think about this in terms of like Thomason's work, this is sort of like the K-theory of Ku, spec of Ku on the locus where beta is 0, right? So this is K of spec Ku on beta equals 0. And so this kind of has this familiar geometric form. There's a category that we can put here no matter what. And now this category has a bounded T structure. With Hart, the finitely generated abelian groups. And what they prove, in effect, is an early form of Barwick's theorem of the Hart, where they use a de Visage-style argument to conclude that the K-theory of this, the connective K-theory, is the same as the connective K-theory of the Hart. So using the theorem of the Hart, you can now conclude that the connective K-theory is the same as the connective K-theory of Z. And this bounded T structure is very easy. This is just the Postnikov T structure. Restricts to, which is a T structure on here already, restricts to a bounded one on here because all of the beta acyclic complexes actually have bounded homotopy, the compact ones. So if you knew that the K-theory of this agreed with the K-theory of Z in negative degrees as well, you would be able to conclude that you got a fiber sequence in non-connective spectra. And so that's kind of the question, how this comes up. And so this is now, of course, I mean, this is a corollary of our theorem that, of course, since Z is Noetherian, the negative K groups of this category do all vanish. And hence, we get agreement with the K-theory of Z. So the other question I kind of want to ask about is also, what is the homotopy K-theory of Ku? So let me just give some, explain this and give a couple other applications of the theorem and then tell you a little bit about the proof. So, questions or comments? Yeah, I was going to say some other examples in just a second. Mm-hmm. So let me just give some examples of some, sort of new calculations that one could make with this in negative and homotopy K-theory of some ring spectra. These were the main sort of goals of this project. So one theorem is if X is a compact space, topological space, R a regular Noetherian commutative ring, then the negative K groups of cochains on R, this is a DGA, this is 0 for n at least 1. So the negative K groups of these cochain algebras are 0 under this hypothesis, and this follows because you can put a bounded T structure on the perfect complexes over such a guy. Regular Noetherian commutative ring. So this is a is one consequence. And then getting back to this, so
this doesn't apply to the continuous functions from X to the reals, with the real topology on the reals.
Offhand, I don't know. I'd have to think about that. David's shaking his head no.
Well, that's just because the reals would be contractible from this point of view. Well, so you get 0.
That's a commutative C-star algebra, so we know what the negative groups are, and they're not necessarily 0.
Yeah, but without taking
Okay. Good question. I will think about this after the talk when I can think. Okay, so another sort of fact is that sort of as a corollary from this is that sort of the negative K groups of KO are 0, periodic KU are 0, little t small mf are 0 for n at least 1 in all of these cases. And this is done by the same sort of trick, to use some localization like this. And the corollary of this, using work of Barwick and Lawson, is that there are cofiber sequences of spectra This is the connective cover of TMF. So these are cofiber sequences of spectra. And now using this, so pi 0 of each of these ring spectra is Z. These are all connective. Pi 0 is Z. And it's possible to define homotopy K-theory of a ring spectra as a geometric realization of some kind of R delta for some kind of spectrum version of the affine line, and a proposition or a theorem that you can prove is that if R is connective, then the homotopy K-theory of R is isomorphic to the homotopy K-theory of pi 0 R. So this is a non-commutative analog. So this is also, due to us, we use this sort of non-commutative affine line. There's a different version. So this is sort of similar to work of Szynski and Kahn in their recent work on sort of A1 invariant, brave new motivic homotopy theory. But their model for the affine line is different. Like actually different, not just a different model. So the results are slightly different. So let me say what that means in this case It means that in all three of these cases, we get a basically complete computation for the homotopy K-theory of these rings. And it's, in my opinion, kind of cool. KH of KO is isomorphic, is equivalent to K of Z plus a suspension of K of Z. And same with the homotopy K-theory of KU and the homotopy K-theory of TMF. I'm writing this in this weird way. So these are all equivalent to KZ plus a suspension of KZ. I'm writing this in this way because there are some natural maps that are not equivalences. So these are abstractly equivalent, but the natural map from KO to KU does not induce that equivalence. So then what this means is that KH of N of KO, or I'm going to do KU, is isomorphic to KN of Z plus KN minus 1 of Z for all N. And this is kind of interesting, right? What did I say pi star KU is? This is Z beta plus or minus 1, where beta is in degree 2. And if beta were in degree 0 instead, this fact would be the fundamental theorem. Right? This would be saying that the K-theory of GM is a sum of the K-theory of the base and a shift of the K-theory of the base if the base is regular. And this gives that same result, but where beta is now in degree 2, and still somehow that pops out just by using these sequences, and then in fact these sequences persist when you join delta, and then this becomes the K-theory of Z. This becomes the K-theory of Z through this equivalence, and then this. And then you can check that the connecting map is, that this map is null homotopic, so that you get that splitting. Well, okay, so that's it with the applications. Any questions? I mean, as far as I know, I don't think that things like this were considered before or proved in some other way, but.
To be clear, since you're using a version of delta,
Yeah.
like over the sphere spectrum.
Yeah. Yeah.
You do not know if that homotopy K theory, if your R is just the algebraic plane spectrum of the discrete rings,
Mm-hmm.
how does it relate to the homotopy K theory of that discrete ring?
I guess it's actually the same. That's one difference between this model and the Szyszynski-Kahn model. This is kind of a flat A1, so yeah. So it's yeah. Yeah, so this is, I guess, in other words, this is the homotopy K theory you know and love. Okay, so now let me give some indications of the proof of the main theorem. So I'll talk about the proof of sort of theorem 2 from theorem 1. In other words, I'm going to assume that we've already proved that the K minus 1 groups are 0, and I want to talk about the proof that the rest of the groups are 0 as well, the rest of the negative groups. Okay, so. And the idea to do this, I mean, this follows somewhat, well-trodden paths, but with sort of exotic brush to hack our way through. Of course, now my notation has diverged from my notes rather badly. Okay. Okay, I'm just going to do this because this is the minimum change. I'll see. Otherwise, I'm going to mess up here. So let's say E, stable infinity category with a bounded T structure. And I'm going to let C be the end completion of E. So this is a stable presentable infinity category. So the example to keep in mind, if X is a scheme, E is perf X, whether or not it has a bounded T structure, end perf X is one model for the derived category of sheaves of OX modules with quasi-coherent cohomology sheaves. So this is the big derived category as opposed to the small derived category. This says end perf X and D sub QCX. So it turns out that a T structure on E induces a canonical T structure on the end completion. So this gains a canonical T structure from the one on E. Of course, it's not bounded. Okay, and so now what we're going to do is we're going to start with this, and we're going to try to find a way to use this hypothesis that k minus 1 is always 0. Oh yeah, let me say that the heart in this case is a Grothendieck-abelian category. So it's something rather large. Okay, so I'm going to make some notation. So sort of the derived category of A1, this is going to be this stable infinity category. Module spectra over the sphere spectrum where I adjoin T as a free variable in degree 0. And this, as we sort of mentioned a moment ago, this is the flat affine line. So this is the one whose homotopy ring is the homotopy ring of the sphere spectrum adjoin a variable in degree 0. So this is not the free E infinity ring spectrum on a degree 0 generator. This is a bit different. So dGm is going to be mod S T plus or minus 1. And now there's also going to be D of sort of, I'll write A1 on 0. This is going to be the kernel of the localization map. And so this is a localization sequence, but now of stable presentable infinity categories. And I'm going to tensor this whole thing with C. Okay, so there's some kind of tensor product on stable presentable infinity categories, and I'm going to use that tensor product, and I'll denote the outcome by dA1 on 0 with coefficients in C, dA1 with coefficients in C, dGm with coefficients in C. And the goal is going to be to cook up out of this sequence a way of reducing the negative K-theory computations of E to something about this side. So let me explain that now. So this, I mean, if we were working over the Z, this would be really exactly the sort of thing studied in Thomas and Trudeau. And you know, it turns out to work with basically no changes over the sphere spectrum, or really over any base rings, E infinity ring spectrum. But okay, Any questions?
So is that finite is any infinity ring spectrum? It's just not free thing.
It is an infinity ring spectrum, but it is not free. That's correct. Okay, so these are all compactly generated, and so I can take compact objects and get something that I can apply K-theory to and give me, and it will give me a cofiber sequence of spectra. So this is exact in the sense that B from earlier applies. And so I get a cofiber sequence of spectra by applying K-theory. So this is a cofiber sequence. And this means that I get long exact sequence in K groups from this.
So just to be clear, so if you just take C, then the compact objects are E?
Right, exactly, yeah. I mean, this, precisely, yes. So if you take the compact objects in C, you just get E back.
Sometimes the sequence is a stand-in for the same, but with E in place of C, but you can't define it directly.
Right, yeah, exactly. I mean, the point is that many compact objects here won't right. I mean, maybe I should say a word about what these really mean. So this is basically the category of endomorphisms of objects of C. So this is endomorphisms in C. That's another stable infinity category, the category of endomorphisms. So it's an object with an endomorphism, and then the maps are sort of commutative squares. This is automorphisms in C. And this is sort of nilpotent endomorphisms, or in nilpotent, or something like that. Okay. Now, of course, many endomorphisms, many compact objects here, won't be, the underlying object of C won't be compact. So, right, I guess just to be aware of that. So let me make some notation here. If I have, so XE will be an object of X, of C with an endomorphism. And now there are some maps between these categories. So for example, I can always actually send E, map E into dA1 on 0 C omega. What is this map? This map takes an object X and maps it to X with the 0 endomorphism. And it turns out that there's also a map back. In the nilpotent case, a compact object does have compact underlying object of C. Okay, this is when it's compact and the endomorphism is nilpotent. I mean, this is something to check. And this composition is clearly the identity. And so this means that, in fact, the K groups of E split off from the K groups of here. Okay, so this implies KE is a summand of K A1 on 0 C. Okay, so now what we want to do is figure out what can hit the homotopy groups of KE when viewed in here. And the point is, in fact, that they all go to 0 here. So there's another map from E to dA1 C omega. This sends an object X to X adjoin T with the endomorphism T. So this is where so as an object of C, this is the direct sum n more than or equal to 0 of X. And T is the endomorphism that just shifts up in this sort of grading. So this gives me a functor from E in. And now look what happens. So I can take a cofiber sequence, T, multiplication by T. This commutes with T. And what's the cofiber of this? Well, the cofiber of this is exactly X with the 0 endomorphism. And that means that all of these objects are 0 in the K theory here, right? Because these have the same K class, clearly. So these objects are all 0. And so using that, what we get is that this composition, what should I call this? This composition, right. So where this is the functor, take the 0 endomorphism. This is null homotopic. Okay, so what have we done? What we've proved is that not only is KE a summand of this, but it's in a part of this that all maps to 0 when we go to A1. And so it's all in the image of the map from KGMC. Okay, so now the stage is roughly set. This is just the best. Right, exactly. So far I haven't said anything new. Yeah, thank you for reminding me. Different Heller. Right. Okay. So what we've done now is show that K minus n of E, or maybe I'll say K minus n minus 1 of E, receives a surjective map from K minus n of GM with coefficients in C. And this will be the basis of the induction argument. Yeah, so I mean, let me just amplify what Chuck said. Yeah, the structure of this argument is not in any way new at this point. What's sort of new will be what happens now. Right. So the goal, clearly, let's imagine what we need to do to prove K minus 2 of E is 0. Well, if we can prove K minus 1 if this is 0, then we're done. If we can put a T structure on the thing that this is the K theory of, then we're done. So the general goal is to prove that, so we've reduced to proving the following. If E has a bounded T structure, with Noetherian heart, then so does this category DGMC omega. That's what this is the K-theory of. Now, it turns out, and I can say this through the experience of writing this paper, that it's pretty hard to put T-structures on things, even when you have a guess of what the T-structure should be. And to do this, we had to actually prove a bunch of new results about descending T-structures over a Verdier quotient. Okay. Now, in sort of the original work on T-structures in BBD, Beilinson, Bernstein, Deligne, there was a lot of work on T-structures sort of through gluing. But that's in a setting where you sort of have six functors type formalism. So that's working on the large derived categories. And then you can often get a T-structure because you have adjoint functors everywhere. But we're taking compact objects, and we don't have those adjoint functors. And it's a lot harder to produce a T-structure in the following situation. So you need to understand you have some kind of localization like E, F to G. These have this has a bounded T structure, bounded T structure. This has a bounded T structure. And this functor is T exact. And you want to understand when is there an induced T structure on G, an induced bounded T structure on G. This turns out to be a somewhat subtle problem, and it's very closely related to the following. Oh, and this is fully faithful, right? And this is F mod E idempotent complete. And it turns out that you can descend a T structure in this way if and only if, so you can do it, if and only if the heart is Sayre inside the heart of F. So recall that a Sayre subcategory of an abelian category is a sort of sub-abelian category that's closed under taking subobjects. And so it's closed under X extensions and so forth, and subobjects. Subobjects is really the problem one. That's the one that it's very difficult to guarantee happens, and at heart, that is where the Noetherianity hypothesis always sort of somehow always comes in. So what else do I want to say about this? So basically, with some difficulty, we check that it works in this case with a Noetherian heart. The proof is yeah, I mean, the proof just requires a bunch of checking that under this hypothesis, for example, there is a T structure on this category, and this sort of thing is T exact, and then there's a T structure on the A1 category, and there's some kind of like Hilbert type argument for that, and then to check this hypothesis. So let me just remark in 1 minute. I mean, you might say, well, maybe you guys just didn't work hard enough. And you could have done this in the non-Noetherian case. And I just want to point out, this structure, this argument, so we do this and then this all works. Okay. So here we have to construct a bounded T structure on dA1C omega. And this is just not always possible. So for example, there exists R regular coherent commutative rings. So you get a T structure on perf R. So coherent means that every finitely generated submodule of a finitely presented module is finitely presented. So Noetherian rings are examples. So there exist regular coherent commutative rings such that R adjoin T is not coherent. And that is exactly, here C would be the derived category of R. And that's exactly saying that the natural candidate for a T structure doesn't actually give you a T structure on this category. So the example that is in the literature, which I found from this book of Serge Laws, is the countable product of these rings. So kind of wild, but if you adjoin a variable to that, it's no longer coherent, and so you can't, for this ring, you cannot perform this type of argument at all. Okay, I'll stop there. Thank you.